lecture for today. So the speaker is Bernd Schulze from the Lancaster group, rigidity group, right?
That's right. Yeah, thank you, and thanks. Thanks to the organizers for inviting me. So this talk will be on joint work with Victoria Kasanitsky, who recently also moved to Lancaster. And what I want to do is I want to present some symmetric versions of some basic results in the theory of scene analysis. So scene analysis is closely related to rigidity theory, but many of you, I guess, will not be familiar with that theory. So I will spend a good amount of time in the beginning of this talk introducing this theory and the main concepts in this theory. But maybe let me give you straight away some intuition of what this is about. So suppose you have a three-connected planar graph, and suppose you embed this graph in the plane with straight edges, straight line segments for the edges. And suppose we think of the interior regions of this planar graph as faces. And the question is, can you lift up the vertices vertically into 3 space so that all the faces remain flat, so coplanar, but at least 2 faces lie in different planes. Okay, so you want to lift up the structure in a folded way, in a sense, but keeping the faces flat. And then you can ask an even more difficult question. You can ask, can you actually lift the vertices up, again, keeping the faces flat, but so that any two faces that share an edge lie in different planes. Okay, so you're basically asking, can you lift up a drawing in the plane to a polyhedral surface with flat faces? Okay, this is the main question of this theory. Right, and so as I said, it's closely related to rigidity theory. In rigidity theory, there has been a lot of work recently on how symmetry in the structure in the bar joint framework, for example, can induce motions in the structure, and often it does. And so now it's natural to actually look at similar questions in this context of scene analysis. And so these results I'm going to present are sort of the first basic results in this context. Right, so here's the quick outline. So we'll introduce the main concepts in scene analysis. Then we will talk about symmetric drawings. So these drawings are sometimes also called pictures. And the main goal in the beginning will be to derive new necessary conditions for a picture or a drawing to be flat, so to have no non-trivial lifting. And we get these necessary conditions by using some basic results from group representation theory. It's really very basic. The main goal is to basically take this lifting matrix and block decompose it using group representation theory. Okay, this lifting matrix somehow plays the analogous role of the rigidity matrix that we have heard about before. So the kernel of this matrix are the liftings of the picture. And then in the second part of the talk, I will talk about sufficient conditions. So the natural question then, once we have these necessary conditions, is are these conditions together with the non-symmetric standard conditions also sufficient for a symmetric picture to be flat, to be non-liftable, okay? As long as it is generic within the given symmetry constraints. Okay, and then we'll finish with some open questions. Okay, so let's get started. So here's the main problem again. So we're starting with a drawing like this. See if this pointer works. Yep, so we have a drawing like this in the plane. We think of this as an embedding of an incidence structure. So an incidence structure is the main combinatorial object that we will be considering. It consists of a set of vertices, of course. So here we have 6 vertices and a set of faces, so subset of vertices. In this case, for this planar graph, we just think of each interior region here as a face. And then, of course, we have incidences of vertices and faces. And the question is, can you lift up these vertices vertically to get a non-trivial lifting? Okay, non-trivial meaning at least 2 faces lie in different planes. In this case, we can actually even do better. I mean, you see that this is actually a projection of a polyhedral, right? So any 2 faces sharing an edge lie in different planes. And this is actually the triangular prism here, okay? So for this structure, we can lift it up. Notice that this structure has reflectional symmetry, right? So here's the reflection line. If we perturb this picture a little bit, so for example, if I twist this in a triangle a little bit, then you can no longer lift it to a polyhedron, okay? In fact, you cannot even get any non-trivial lifting. Okay, so this is really a symmetry-induced lifting, and I will explain how to see that. Okay, so this scene analysis theory has nice connections with rigidity theory, and I will briefly mention those. And it also has nice practical applications, which is important when you want to make impact, right? So in particular in computer vision and artificial intelligence, this has important applications. Basically, you want to be able to reconstruct polyhedral surfaces or polyhedral objects from projections, okay? And so this is well studied in this community. So let me tell you a little bit about the history of this theory. So originally, these problems were studied in the computer vision community, and the pioneers were, well, the main pioneers were Mackworth and Hoffman. So they used labeling schemes and reciprocal diagrams to get necessary conditions for drawings or pictures to be flat, to be non-liftable. Note that reciprocal diagrams actually go back much further. They were not invented by Mackworth and Hoffman. They were invented by Maxwell and Cremona a long time ago. And so this is where the nice connection to rigidity comes in. So let me tell you briefly about this connection. So suppose you have a bar joint framework, and suppose you have a self-stress in this framework. Okay, so you have forces in the bars of the framework, that at every vertex, at every joint, the forces balance. Okay, they add up to 0. That means at every vertex, you can actually build a polygon of these forces. And if you then reassemble these polygons, you can actually get a dual structure of your original bar joint framework, so that all the new edges are perpendicular to the original edges. Okay, and this is called the reciprocal diagram. So you can check for stresses in frameworks by using these reciprocal diagrams. This is what Maxwell and Cremona did. That is statics with these things. But the same diagrams actually show up in this lifting context. So if you have a picture and you have a lifting to a polyhedron, then you can record the gradients of those faces of this lifted structure as points on the plane again, and that way you can actually again get the same reciprocal diagram. Okay, waving my hands here a little bit, but the same reciprocal diagram comes up in this way. Okay, so if you have an abstract spherical polyhedron, and you think of it as a bar joint framework, suppose there's a self-stress. That's true if and only if there exists a reciprocal diagram, if and only if you think of the structure as an incident structure, there exists a lifting of that structure to a polyhedral scene. Okay, so there's a very beautiful theorem of Maxwell and Cremona that links these topics. Okay, I will not talk too much about reciprocal diagrams, but I thought it's nice to mention because rigidity workshop. So there's one of the connections. Okay, if you don't have a planar graph or an abstract spherical polyhedron, then actually the story becomes a bit more complicated. So reciprocal diagrams in general do not give you sufficient conditions for the realizability of a picture as a polyhedral structure or polyhedral scene. Okay, so people continue to study these questions using different methods. So Sugihara used linear programming methods. Whiteley and Crapo used basically projective geometry to study this. And then this lifting matrix was constructed. So this is some of the key tool that I'll be talking about in this talk. So the lifting matrix has the property that its kernel is the space of all liftings of a given picture. Okay, and since we know it's easy to check what the dimension is of the space of trivial liftings, so you get immediate necessary conditions for a picture to be flat, to be non-liftable. Okay, the same way as you can check that a framework has certain necessary conditions to be rigid using the rigidity matrix. Okay, so what is a trivial lifting? Of course, if I have a picture in the plane, I can just lift everything up, keeping all the vertices planar. Right, that's sort of the trivial thing you can do. And then, of course, you can tilt it in various ways. So, but this is easy to count the dimension of that space of trivial liftings. Okay, so we have necessary conditions from this matrix, and then following a conjecture of Sugihara, Whiteley actually proved that these necessary conditions are also sufficient for a picture to be flat, as long as the picture is generic. Okay, so the points are generic enough. Okay, so this will be the starting point of this talk. I will derive new necessary conditions in addition to the standard ones if the picture is symmetric, and then we will look at sufficient conditions. Okay, so notice that if you have symmetry, of course, you no longer have a generic structure, right? Symmetry is a special geometry, and so this example that I showed you in the beginning is an example where Without symmetry, this has no lifting, no non-trivial lifting, but with symmetry, actually, it becomes liftable to a triangular prism in this case. Actually, since this is a planar graph here, you can also just use rigidity and say, okay, this has a self-stress, and because it has a self-stress, it has a reciprocal diagram, and so you can actually lift it up, okay? But in general, it's more complicated, so you may have a non-planar graph, for example. Okay, so again, we want to have necessary conditions and then sufficient conditions. So when I say minimally flat, so I'll be interested in this talk in non-trivial liftings. So at least two faces should be in different planes. That's non-flat, so that's non-flat or liftable. Minimally flat means that it's flat, so you cannot find such a non-trivial lifting. But if you remove any incidence, then it actually becomes liftable. Okay, so it's flat without any redundant constraints, so to speak. So you can think of this as isostatic, if you wish, for the rigidity people. Okay, so let me formally introduce the main objects. So, yep. Not completely obvious, no. But you can do the counts, basically. So that you can, there's an overall count you can check, and I will give you that count, on the number of vertices, incidences, and faces, basically. And then you have sparsity counts. So you have to check every substructure as well. If they hold, and the structure is generic enough, then it will be flat. Okay. Actually, this is not generic. It's still threefold symmetry, I guess. But it will still be flat. And in fact, I mean, this is going to be the topic of the second part of this talk. So I will look at threefold rotational structures, and I want to have a characterization of those structures that are flat. Okay, so no, it's not true. I mean, maybe for such a small structure, you can maybe play around with it a bit, and you can see it. Yeah. Yeah, basically, yeah. Yeah. Okay. So let me introduce the main notions. So an incident structure is just the polyhedral, the combinatorial object. So you have a set of vertices, abstract set of faces, subset of vertices, and you have incidences, so a subset of this Cartesian product, V and F. Picture, so in D-1 space, so D will usually be equal to 3, so picture in the plane or a 2 picture is usually what we will consider, but you can of course do this in an arbitrary dimension. So that's an incident structure that is embedded in D-1 space, okay, so usually in the plane. So you give coordinates to the vertices. A scene, or a polyhedral scene sometimes called, is again an incident structure, but now you have two location maps. So one map, little p, that gives you an embedding of the structure in d-dimensional space, in 3 space usually, and then another map here, p, that assigns faces basically, planes to the faces. Okay, so for every face you want to keep the face flat, so you have to somehow assign a plane where this face lies in. And this is done by essentially assigning a normal vector to that face. Okay. Actually, I mean, the normal will always be such that the last coordinate is equal to 1. Oh, this doesn't work very well. So the last coordinate is 1. We don't want to have any vertical planes, basically. That's what this is saying. And this d, this last coordinate there, is just the constant in this equation here. Okay. And then, of course, the lifting of a given picture as R is just such a D scene, so that if you project it down to the plane, that's the original picture again. Okay, so this is exactly the example I gave you earlier. And lifting is trivial. Well, if all the faces lie in the same plane, so that's not interesting. And if not, it's non-trivial. And if you can actually manage to get any two faces sharing an edge in different planes, then it's a sharp lifting. Okay. And a picture is sharp if the lifting is, if there's a sharp lifting, etc. Okay, so now suppose you have a picture on an incident structure, and you want to know whether you can lift it, right, to a non-trivial scene. So what do you have to do? You have to find one new coordinate for every vertex, because you're lifting the coordinates into the next higher dimension. Okay, so those are your zi's here or here, one coordinate for each vertex, and then you have to find well, planes for your faces, right? So these are the variables that we have, and we just order them so that we first have the coordinates of the points and then the normals, basically, for the faces. And, well, of course, we want to have these linear equations satisfied, right? If a vertex I is incident to a face j, then that vertex should lie on that face, so this equation is satisfied. It's just a very simple linear equation, so we have this system of linear equations. Look at the corresponding matrix, and that's exactly the lifting matrix. Okay, so the kernel of this matrix is the space of all liftings. Okay, so that immediately gives you some necessary conditions for a picture to actually have a lifting. Okay, so we know that the space of trivial liftings is of dimension d. Okay, so if the number of constraints is number of columns of your lifting matrix minus d plus 1, then you have a d plus 1 dimensional kernel, so one non-trivial motion must be, one non-trivial lifting must be in the kernel. Right, so you know it has a lifting, and if you can actually also verify the subgraph counts, you can show, well, Walter Whiteley showed that actually you have a sharp lifting. Okay, so any two faces lie in different planes. Okay, and well, so if you only care about independence, then well, you really want to check these sparsity counts. Okay, again, d is the space of dimension of the space of trivial liftings. So we will be interested in minimally flat structures. So we want to have this overall count. Okay, so the lifting matrix has maximum rank, so to speak, and we want to have these subgraph counts. Okay, so it's easy to show that these are necessary conditions, just looking at the lifting matrix. But then Walter actually showed that they're also sufficient if your structure is generic, and that's actually a non-trivial result. So this is actually one of the key theorems in scene analysis, similar to Larman's theorem, for example, in rigidity theory. So we want to symmetrize that. Okay, so let's look at symmetric pictures now. Just a few more notions here, very straightforward. So if you have a symmetric picture, well, so let me define a symmetric picture. So first of all, we need to define an automorphism of the underlying combinatorial structure, which is this incidence structure. So this is a pair of permutations, pi and sigma. So pi is permuting the vertices, sigma is permuting the faces, and of course, an incidence VF. Well, VF is an incidence if and only if pi v and sigma f is an incidence. Okay, so you have permutations that preserve the incidence structure, basically. Very natural definition. Of course, the automorphisms form a group. Denote this by odd s. And then an incidence structure is symmetric with respect to a given group if the group acts on that structure. Okay, so if you have a homomorphism theta from the group to this automorphism group. So what is a symmetric picture then? Well, you have another map here, tau, which assigns an isometry of d minus 1 space to each group element. And this just says that each of these isometries here is actually a symmetry of the structure. Okay. So, for example, tau of gamma could be a reflection that preserves the structure, or a rotation, or something like that. Okay. Right. Yeah.
What about like permutations that we label elements in some space, so it's considered a symmetry of the structure?
Yeah, but you need to have an isometry of the underlying space that does that for you, right? So you can have symmetries of the combinatorial structure, but I'm interested in the geometric symmetries, right? So I want to have, for example, a reflection, and then the reflection somehow should observe the underlying automorphism. Yeah. Okay, so necessary conditions for symmetric pictures. How do we get new necessary conditions? So I said we need some representation theory, very basic stuff, but the main idea is that you take the lifting matrix and you use representation theory to block decompose this matrix. Okay, and then for each block, well, the trivial lifting space also decomposes, so you can actually do sort of a counting argument for each block. Okay, so you break up the problem into independent subproblems, and each block will give you added information, basically. That's the main idea. So let me tell you how this works. So here's a symmetric picture. I have to introduce various representations of our given group of the structure of the picture. So first of all, I take this PV. PV is just a permutation representation of the vertices. Okay, so each PV of gamma here is a permutation matrix, a V by V permutation matrix that tells you how the vertices are permuted under this group element. I do the same for the faces. So PF is a permutation representation of the faces induced by our map theta. And well, similarly, I can do the same thing again for the incidences. Okay, and this permutation representation PI for the incidences we call the internal representation. Okay, it tells you how the incidences are being permuted under the group elements. And then we also need an external representation. That's a little bit more complicated. So the external representation is this one. So first of all, you take the permutation representation for the vertices. Okay, so if you look at the matrices for this thing, you have sort of a first block matrix corresponding to the permutation of the vertices. And then you have a second block matrix that looks like this. This starts off with a permutation matrix for the faces. But then, so that's a 0, 1 matrix. But then you replace every 0 by a D by D 0 matrix, and every 1 by this matrix. So where you have the isometry of the group element here, and you just augment it with this one. Okay. So this may look a bit strange, but I mean this is what we need to get this block decomposition. Okay. So we have this internal representation and this external representation, and with these representations we can show this theorem. Okay. We can show that the lifting matrix MSR of a symmetric picture actually intertwines the internal and the external representation. Okay, so if you multiply the internal representation from the left, external from the right for any group element, then this equation holds. Okay, and then basic representation theory tells you, as an immediate corollary, it's basically Schur's lemma, tells you that you can block decompose this lifting matrix if you choose appropriate coordinate systems. Okay, and that's very nice because now we really broke down the problem into independent subproblems, namely one for each block, where each block corresponds to an irreducible representation of the given group. Okay, so this is where our new necessary conditions come from. So let's see how that works. So by the picture theorem, we have the standard non-symmetric necessary condition immediately obtained from the lifting matrix. So now this block decomposition gives us more conditions. I need to give one small lemma before I can state the symmetric counting rule, basically. This lemma says that if you look at the space of trivial liftings, okay, that's actually an invariant subspace for the external representation. Okay, so we can look at the complement space, basically. Maschke's theorem tells us there's an invariant complement space. Okay, and so this is the symmetry extended counting rule. Okay, so we have a symmetric picture, and well, if this picture is minimally flat, then this character equation is satisfied. Okay, remember, a character just records all the traces of the representation matrices. Okay, so this is a vector equation, and we have one equation for each group element. Okay, now why does this hold? Well, basically, you look at your lifting matrix. Okay, you restrict it to this complement space of the trivial lifting space. Okay, and because your picture is minimally flat, that means that this restriction of the lifting matrix as a linear transformation to this complement space is actually isomorphism from the space R to the I. Okay, so the space corresponding to the incidences to this space, well, to this complement space Q. Okay, and so of course this intertwining property is still holds. So that means that well, the internal representation is equivalent to the external representation restricted to this complement space Q. Okay, and therefore they have the same characters. Okay, very rough proof. So that means that this character is the same as the character of this external representation restricted to the complement space. But that character is the same as the character of the original representation minus the character of this trivial motion space. This is the complement space. Okay. Yeah, it's really quite simple representation theory. Okay, so now the point is that this is actually very easy to compute. Okay, so look, for example, at this character here, so chi of pi. what does it do? So it records traces of the permutation matrices, right? So if you look at the identity element in your group, then this is just the I by I identity matrix, okay? So the trace is just the number of incidences that you have. And then you look at another non-trivial symmetry operation, element in your group, then what is the trace? Well, you get a trace, a non-zero contribution to the trace, if and only if you have a 1 along the diagonal, right? And when do you have a 1 along the diagonal? Well, if that incidence is fixed under that symmetry element, right? If your incidence is not fixed, then you get a pair of 1s off the diagonal. Okay, so really, all you have to do is to compute this character is count the number of fixed incidences under symmetry operations. That making sense? And similarly here, so PV is again just a permutation representation. So you just count the vertices that are fixed under various operations. And again, they do the same for faces. And this tau hat is just, well, it's just an isometry of, augmented by a 1, basically. Okay, so this is easy to compute. So we can rewrite these equations in the following way. So I have a new notation here. So V gamma is just the number of vertices fixed or unshifted by the element gamma. And similarly for F and I. And then these character equations that you just saw is just, well, can be written as these equations. Okay, one equation for each group element. I will give an example in just a second. Okay, so in dimension 2, so for D equals 3, so for 2-dimensional pictures, you get very simple added necessary conditions. Okay, so if you look at the identity element, you just recover the original non-symmetric count. But if you have a half-turn present in your picture, then you get this added count. So if your picture is minimally flat, the number of fixed incidences by this half-turn is equal to the number of vertices fixed by the half-turn. In other words, the vertices that lie on the rotation center minus the number of faces fixed by the half-turn plus 1. Okay? And similarly, if you have a reflection S, or if you have a higher order rotational symmetry. Okay, so it's really quite amazing how simple these conditions become after you do this bit of machinery here. So let me give you an example of how this all works. So I start again with the same example that I showed you in the beginning. So this is a picture with a reflectional symmetry, right? And if you do the non-symmetric counts, okay, so Walter Whiteley's counts, then, well, you look at the number of vertices, faces, and incidences, and you check, well, actually this overall condition is satisfied. You check the sparsity counts, well, yeah, it's generically flat, okay? But now let's go back to our, to our new counts. So we have a reflection here. So this equation must also be satisfied, okay? So maybe you can remember that. So IS must be VS plus FS minus 1. So what is IS in this case? What is a fixed incidence? So remember my faces here are just these interior regions. So fixed incidence is, for example, this vertex and this face, right? Because the vertex and the face is fixed under this reflection, they're unshifted, right? They both lie on this reflectional line. So this is a fixed incidence, okay? But there's no other fixed incidence. Because, I mean, this face is fixed, unshifted, but no vertex here incident with that face is fixed. Okay, so we have IS is equal to 1. We have 2 fixed vertices. We have 2 fixed faces. Okay, so this is 2 plus 2 minus 1 is 3, but 1 is not equal to 3. Okay, so just from that we know already that this must have a non-trivial lifting. Okay, very simple counting, which is nice, and you can do this for more complicated structures. But we can, of course, also write down the full characters, and let me do that, and we gain a bit more information if you do that. So the irreducible representations of the reflectional group, well, it's just 1, 1, and 1 minus 1, a well-known fact. So here is the external character minus the character restricted to the trivial space. So how do we compute that? Well, since our group has 2 elements, right, our character will have it's just a 2-dimensional vector. So if you look at the identity element in the group, right, then what do we have to count here? Well, PV, this will just be the V by V identity matrix, right? So we have V, and F is again an identity matrix, F by F, so we get F, and tau hat for the reflection is just, for the identity is just 3 by 3 identity matrix. So we have v plus 3f, which is 18, okay, for the first trace here. And then if you look at the reflection, well, we have to count the number of vertices that are fixed, number of faces that are fixed, and number of faces that are fixed we have to multiply by the trace of this guy, but this is just 1, okay? So we just have that, and this is 4. So very simple calculations. And then we also have to compute these characters, but there's a little lemma that says that the character of this messy stuff is actually the same as the character of this tau hat, okay? And tau hat can be written down immediately. So it's just 3, 1. Okay, so our character is 15, 3, and any representation can be written as a linear combination of the irreducible ones. So let me do that, okay? And then we do the same thing for the internal representation, right? We compare these two. For the internal representation, just have to count incidences that are fixed, right? Under the identity, all of them are fixed. Under the reflection, there's this 1. So we get this character, and as a linear combination, we get this, okay, for the irreducible ones. So now we just compare the coefficients here. Right? The coefficients tell us what the dimension of the corresponding invariant subspace is. And we see that this invariant subspace is of dimension 9, and this one is only of dimension 8. Okay, so there's one more degree of freedom with respect to that symmetry rho 0 than we have constraints. Okay, so we know there's, not only do we know there's a lifting, but we know the lifting will be actually symmetric with respect to rho 0. And rho 0 is just the trivial representation, so it's a fully symmetric lifting. Okay, so you can lift this up, preserving the original symmetry of the structure. Okay, so looking at these character counts, you can actually get quite a bit of information about what's going on. Yeah. The what? Sorry. Oh. Actually, I could include if I want to. Actually, this is just 3 vertices, so it's sort of trivial in this case. But I don't have. Yeah, I don't have to. I could. You know, you just define your faces as you like. It's just an incidence structure, so you just have vertices, faces. Of course, you want to choose something that somehow counts to be flat without symmetry. Otherwise, it's not interesting, I suppose. But yeah, that's just an example. So I could also just remove this face, for example, because yeah, you have 3 points. You can always get them coplanar, actually. So you can just work with F1, F3, and F2, and you will get the same result, actually. I mean, this is a very simple example, right? But I mean, I hope you see that the counts are actually very, very simple for more complicated structures. Okay, so some more examples. Yeah, so these are still minimally flat, even with symmetry, and these are not, sort of fairly easy to see for these small examples. But okay, so you can do these counts for all sorts of groups, just counting numbers of fixed structural components. And maybe one more comment. So I did everything now for 2-dimensional pictures, but of course you can do everything also in arbitrary d dimensions. So you may want to lift a 3-dimensional picture to a 4-dimensional space or something like that. But it's maybe less important for practical applications, but nevertheless maybe interesting. And we have also some other operations where you can take minimally flat pictures in the plane or in D space to the next higher dimension using this coning operation. So here again, the faces suppose are just the interior regions. Doesn't have to be, but let's say those are the ones that we're interested in. Then we just cone this structure. So we just add a vertex, link it to every previous vertex, and then this face becomes this 3-dimensional face, okay, etc. And then this, you can show that this structure will again be minimally flat if this one was. Okay, so there are constructions that can take minimally flat pictures to higher dimensions that are also minimally flat. Okay, but that's a bit on the side. So now I want to go to the second part of the talk. So the natural question, of course, is now if you have a picture that satisfies the standard counts together with the added symmetry counts, is that sufficient for the symmetric picture to be flat, right? As long as it is generic within the given symmetry. And that's, well, that requires a different technique. So this is really just combinatorics now. And it's actually a more difficult problem. So we have this conjecture. So this conjecture says that, in fact, for all dimensions in all groups, we conjecture that the non-symmetric counts together with the symmetric counts are sufficient for a picture to be minimally flat. Okay, so here we have the standard non-symmetric counts. This just says, well, the counts I just showed you are satisfied. And then you have to be careful for all subgraphs, or for all substructures with possibly a smaller symmetry group. For that group, again, if the structure has this overall count, again, the added symmetry counts have to be satisfied. Okay? And we were able to show that this conjecture is true for d equals to 3, so this is somewhat the most interesting case, and for this threefold rotational symmetry. Okay, so this is the first case. We haven't been able to extend it yet, but this is the first main result, combinatorial result, I guess, in this theory. And this is so. For the rest of the talk, I want to sketch the proof of this result. Okay. So if d is equal to 3, okay, then well we have these conditions: v plus 3f minus 3 in these sparsity counts, and the symmetry condition that I showed you earlier reduces to something very simple. It just says that the number of incidences fixed by the threefold rotation is equal to the number of vertices fixed by the threefold rotation. Okay, so either you have no vertex on the rotation center, and then you also have no fixed incidence, or you have one vertex that lies on the center, and then you must also have a face that is fixed containing that vertex. Okay, it turns out that we actually don't have to care about the third condition. The third condition is already implied by the second condition in this particular case. Okay, so what is the proof sketch? So the main idea is that if we have a general incidence structure with threefold rotational symmetry, we reduce it to the case where every face actually has 4 vertices. So we reduce it to the case where you have a 4 uniform hypergraph. Why do we do that? Well, first of all, this overall count here reduces to just f equals to v minus 3 if every face has 4 vertices, okay? Because in that case, I is 4f, so you just subtract that and you get this. Okay, so if you have 4 uniform hypergraphs, you're interested in 1, 3 tight hypergraphs, which are graphs satisfying this overall count, and for every substructure, you have f prime at most v prime minus 3. Okay? And then Tibor Jordan and Victoria Kasanitsky showed very recently, well, they gave a characterization of 1, 3 tight, 4 uniform hypergraphs in terms of a recursive construction. Okay, so they have 3 moves that they call J extensions, J from 0 to 2, and they can actually build up these 1, 3 tight hypergraphs from just a single hyperedge. Okay, so this is the result we want to use. So we want to symmetrize this result, right? So we wanted to do a proof by induction, basically, and say you have your symmetric incidence structure. You want to find low-degree vertices, and then we want to do like an inverse of these J extensions, so a J reduction, but a symmetric one. So you get down to another symmetric structure with fewer vertices, and then show that our counts are still satisfied. Use the induction hypothesis, and then we have to. So then we can show it's minimally flat. And then we want to do these extensions again, the symmetric extensions, to show that the original structure was minimally flat. Okay, that's the main strategy. And the key problem is actually to reduce symmetric structure, to remove vertices of low degree in a symmetric fashion, so that all the counts are still satisfied, the non-symmetric count and this added symmetry count. That's the main problem of this proof. Okay, so once you have reduced your structure, we do the symmetric extension again, so the reverse operation, so to speak. But that's easier because we can just start with a lifting matrix that has maximum rank, and then we do these extensions, and we just have to show that independence is preserved. So again, you have maximum rank. Okay, so the combinatorial problem is really in reducing a structure symmetrically. Okay, and once we have done that, well, then we just generalize our result from 4 uniform hypergraphs to general incidence structures with faces of arbitrary size. But again, this is just a lifting matrix argument. We can just move vertices one at a time back into the original faces and see that the rank doesn't change. Okay, so right, let me walk you through this a little bit. So first of all, we have to reduce the problem to 4 uniform hypergraphs. So maybe I can. It's a very simple operation. I can maybe show you how that works. So let's look at a face in our three-fold symmetric structure. Of course, then if you have one face, you have a whole orbit of faces, right? Orbit of size 3. And you have a bunch of vertices in here, and of course symmetrically in here. Yep. And so you just number the vertices in one of in a representative of this face orbit. So let's say 1, 2, 3. And well, now we want to create faces of size 4. So we choose these first 3, and we add one more. And that's our first face with 4 vertices. And then again, we keep the same 3 here, but then we add another one here, another face with 4. And we keep doing that, and then you do the same thing symmetrically in the other faces. Okay? So you're extracting a 4 uniform hypergraph from this incidence structure. Oh, and then if you have a fixed face, so let's say here's your rotation center. Here's a face that's unshifted. You can always find 3 vertices in here that are not fixed. Okay, so this becomes your 1, 2, 3. And then you do the same thing, basically. You take these 3 and always add one more to that to get a face of size 4. Okay? So that's our 4 uniform hypergraph that we can work with. And this lemma is important because it says if you have an incidence structure, a general incidence structure satisfying our non-symmetric counts and this added symmetry count, well, then you can do this construction to get a 4 uniform hypergraph, and it actually is still satisfying all these counts. Okay? So it's still going to be 1, 3 tight, which is the analog of this count, and your symmetry equation is still satisfied. That's easy to show, but it's important because now for the combinatorics we can just focus on 4 uniform hypergraphs. Right? If you have an arbitrary incidence structure, you want to show it's minimally flat. Just derive this 4 uniform hypergraph, show that is minimally flat, and then in the end you just do a little argument with the lifting matrix, sort of moving the vertices back into the original faces one at a time, preserving the rank. Okay, so from now on we can really just focus on these nice 4 uniform hypergraphs. Okay, and again for those hypergraphs, so Tibor and Victoria have this nice characterization, recursive characterization, with 3 operations. So let me show you how these operations look like. We will then have to symmetrize these operations to make it work for our proof. So the first operation is very simple. So you see a 4 uniform hypergraph on the left. You identify one vertex V, and you add one new edge, E, that contains V and a new vertex Z. Okay, so you just add one more hyperedge. That's it, and one vertex. Preserves the counts. The second operation is similar. So you identify a vertex V again in some face, and you add a new vertex Z, and again you add a new face that contains V and Z. But then you do one more thing. So you delete this in hyperedge that contains V. You throw V out and put Z in. Okay, so E1 is replaced by E1 minus V plus Z. Okay, that gives you a new 2-valent vertex Z. Okay, or degree 2 vertex. And then, of course, similarly, you can get a new degree 3 vertex. So again, you add a new edge here containing V and Z. And now you remove 2 edges, and you throw V out and put Z in. Okay, those are the 3 main constructions that you need to characterize 1, 3 tight 4 uniform hypergraphs. Okay, so what we need is, we need symmetric versions of these things. So how does that work? Well, it's very simple. So suppose you have a vertex U you want to reduce with these moves. Okay, but you don't only want to reduce U, you want to reduce the whole orbit, right? Because you want to reduce it to another symmetric structure to apply your adduction hypothesis. So you reduce U on some vertex V, okay, and U and V must be such that there's only one edge that contains both of them. And once you have reduced U on V, then you reduce gamma U, which is the image of U under the 3-fold rotation, on gamma V, and then you do the symmetric thing again for gamma squared of U, and you reduce it on gamma squared of V. Okay, so an example is shown here. So here's a 4 uniform symmetric hypergraph, and well, now you do your 3 reductions. So I think V in this picture is A1, I guess. So I reduce U on A1, gives me this. And then I think I'm reducing gamma U on gamma of A1. And it gives you this. And then you do one more reduction, you get here. Okay, so you go from a symmetric structure to this structure. Notice that this is a 1 reduction. Okay, this is also a 1 reduction. This is just a 0 reduction. Okay, here I'm just removing an edge. But here I'm removing that edge and I put in another edge here. Okay, so it doesn't matter what happens in between. The key is that you go from a symmetric structure to another symmetric structure. Okay, using these non-symmetric reductions. And you can show that actually if you do that, then the symmetry is preserved. Okay, you can also show that if you have a 1-3 tied to a 4 uniform hypergraph, there will always be a vertex of low degree. Okay, so of degree at most 3. So now you can do your induction on one of these low degree vertices. And there are different cases to consider now. So if you have the case that U and all images of U, so the whole orbit of U, is incident to 3 faces, then you can very easily remove those edges to get another 1-3 tied 4 uniform hypergraph, satisfying all the counts. So maybe let me show you how that works. So here's our U. So here's U. Gamma U is our image, gamma squared of U. So what could happen? So U could be just in one face, and then so gamma U symmetrically and gamma squared of U also just in one face. And in that case, you can just remove that face with that vertex, remove that face, remove that face. All the counts are still satisfied. It's sort of trivial. And of course, your symmetric condition on the number of fixed incidences and vertices is also satisfied because I didn't touch anything that was fixed. Okay, so this is the easiest case. You just remove it and you're okay. Okay, but it could also be that you have this picture. So again, U, gamma squared U. So it could be that it looks like this. So you have a face containing U, but it also contains gamma of U. And then symmetrically this and that. But again, so this is the case when the degree of U is 2, but the degree of the whole orbit is still 3. Okay, but that's also okay because I basically just already showed you that case. You can just remove these, and again, all the conditions are still satisfied, so you can apply your induction hypothesis. Okay, it gets tricky when you have no vertex of degree 1, and you don't have a vertex of degree 2 of this type. So if you have a vertex of degree 2, and well, the degree of the whole orbit is 6, right? Then your picture is basically this, right? You have 2 faces for every vertex in the orbit, and now what you have to do is you have to do a 1 reduction on this. Remember how the 1 reduction works? You remove one face, and you remove this other face, but you have to add a new face that doesn't include this vertex, but another one. Okay, so basically you have to add another face when you remove these 2. Okay, that's okay, but now you have to make sure that we can, do the same move symmetrically for the next one. Right? We do a reduction here, but this reduction now has to be the symmetric version of this reduction. Okay, so if we add this, we do a reduction here, that face that we add must be the symmetric copy of that added face. And that may go wrong. Okay, and even if that works, you still have to do, again, the symmetric reduction on this and make sure that you can put in that hyper edge. Okay, so this is where the difficulties arise. You have different types of blockers for these reductions. There could be a blocker that already happens here, or maybe this is okay, but then we have a blocker here, etc. Okay, so this becomes tricky, and it becomes even worse if you have, if you have a vertex of degree 3, so no vertex of degree 1 or 2, but only vertices of degree 3, and then, either you have this situation where you have 3 faces here, and 3 faces here, and 3 faces here, right? Then you have degree 9 overall. Then you have to do 2 reductions, and you have to do it symmetrically again. So you have to add 2 faces here, 2 faces here, 2 faces here, and all that symmetrically. Okay, so that becomes quite technical, so I will not go through that. Okay, in the last case is degree 3 and overall degree 6. Okay, but this all works, so you can reduce everything nicely to these base graphs. So either you have a single edge left, symmetric of course, or you have these three or these three left. And so here's the theorem. So a 1-3 tight hypergraph with this added symmetry condition. So H is a 1-3 tight hypergraph with this added symmetry condition, if and only if you can construct it from one of these base graphs using these symmetric extensions. Okay, so we have a recursive construction for these types of graphs that we're interested in. So what's left to do now? We have to show that the base graphs are minimally flat, and then we have to show that whenever we do a symmetric extension, the lifting matrix still has maximum rank, right, or preserves independence, and then we're done. So that's a very small geometric argument that's left. Obviously, each one of these base graphs is minimally flat. I mean, if you just have one face, there's only a trivial lifting. And you can easily check that the other ones are also minimally flat. So this is what I just said. We just now have to do an argument on the lifting matrix that shows that these extensions preserve the rank, okay, the full rank. So the way we do that is we just show that each non-symmetric extension preserves the rank. And if you want to do a symmetric extension, you just apply the argument 3 times, basically. Okay. So we really just have to focus on the non-symmetric extensions, the one that Thibault and Victoria came up with. So that's the theorem. So you have a 4-uniform hypergraph, and you do a J extension on that. Okay, so on some vertex V. So Z is the new vertex here, and well, we can make this theorem work. All we have to do is we have to find some realization of the new vertex so that the new structure is still having an independent lifting matrix. And what we do is to obtain that realization is we put the new vertex at the same position as this vertex V. Okay. Here's a very brief summary of the proof. It's a very simple proof on the matrix. Okay. So you start with this lifting matrix of H of the original structure. Okay. So that's the matrix where you ignore the last 4 columns and you also ignore that column. Okay. So you just start with the lifting matrix. So what do you have to do? Well, you add a new vertex, right? And you also add a new face. So you have to add a new column for that vertex. Let's make it all 0 first. You add a new edge. So you have to add D columns, all zeros at first. That, of course, preserves independence. And then we have to add, well, first we add VE, AE, and BE. Okay, so 3 incidences for this new edge. And that gives us zeros for the Z column because that is not involved. And we get these entries for the newly added D columns for this new edge. This preserves independence because we assume that these are not collinear. Okay, so they are finally independent. Preserves independence of the whole matrix. Then we add this incidence ZE. Again, that preserves independence because it's going to be the only one where you have a 1 in the first column. And then we have to replace the V, comma EI by this new vertex Z and EI prime. Okay, and that you can do by just taking VEI and you subtract VE and add ZE. So you just subtract this row, add this row, and because of this position of this new vertex, you actually get the row that you want. Okay, this is actually very simple. So independence is preserved, which means that we really proved our theorem for the 4-uniform hypergraph case. Okay, so as a corollary, or as a summary maybe of what I've talked about in the last 20 minutes or so, we have this. So a C3 symmetric 4-uniform hypergraph is generically minimally flat if and only if it is 1-3 tight and satisfies this extra condition on the fixed incidences and vertices. Of course, the only thing that's now left to do is we have to go back to an arbitrary incidence structure, right? Because this is a special case only where every face has 4 vertices. But again, I said this earlier, this is again a very simple lifting matrix argument. So how do you get the original incidence structure if it was not 4-uniform? Okay, so you have faces with lots of vertices maybe, but you can do sort of this reverse process that I did here. Okay, so moving vertices from these faces of size 4, moving back into the original face, and you can just track what happens in the lifting matrix, and you see the rank is preserved. Okay, so that really proves the whole theorem. Okay, so that's almost it. I have one last slide, or maybe two. So I mentioned at the beginning, so what I've done so far is we looked at minimally flat pictures, right? So pictures that cannot be lifted to any non-trivial lifting. What is often interesting in applications is whether you can actually lift it to a polyhedral scene, right? To a sharp polyhedral scene where any two faces sharing an edge actually lie in different planes. This is a stronger lifting property, really. And we also have some results on that. So lifting is sharp if each pair of faces sharing sharing a vertex, actually. I think I used to say edge, but okay, lie in different planes. I think you know what I mean. And well, so Walter's picture theorem gives a characterization for all sharp liftings, non-symmetric ones. Okay, so we want to symmetrize that again. A key ingredient in Walter's proof is that you can characterize all independent pictures, okay, generically independent pictures. So we have to sort of give an analog of that in the symmetric case. We can't quite characterize all independent pictures with C3 symmetry, but we have some sufficient conditions. Okay, so if the incidence structure satisfies this count for every subset of incidences and this, then we can actually guarantee that the structure is independent. Okay, and so we can use this to symmetrize Walter's proof, and we get some sufficient conditions for symmetric pictures to be sharp. Okay, to be liftable to polyhedrons, really. And this is the theorem. So if you have your incidence structure so that you have this stronger sparsity count, so V plus 3F minus 4 instead of 3, then, well, if no vertex is fixed, then you're guaranteed you have a sharp lifting. And if this symmetry condition holds and that, then again, you're guaranteed to have a sharp lifting. Okay, so this is interesting for applications, I think, because people want to know if you really can lift it to a polyhedron rather than just some non-trivial folded image of a picture. Okay, proof idea is very similar to Walter's proof idea. We just sort of again symmetrize that using this theorem. Okay, so final slide. Let me just tell you a little bit of what's open now. So of course you may wonder what do you do for other groups, and this is still completely open. The problem is that our proof technique doesn't extend. So, for example, if you look at a half-turn symmetric picture, okay, so a picture with half-turn symmetry, then you want to do sort of the same thing. You want to extract that 4-uniform hypergraph, right? But the problem is that you can do that, but the 4-uniform hypergraph you get will have different lifting properties, unfortunately. So here's a very simple example. So let me draw you a twofold symmetric picture. Okay, so my twofold rotation center is here. Okay, and suppose I just have one symmetric face and 5 vertices. That's minimally flat, right? All I can do is I can lift this up, sort of trivial. Now I want to extract a 4-uniform hypergraph. So what can I do? All I can do really is I can choose this, and I can choose that. Right? It should be symmetric. But now, of course, this I can lift, right? This sort of becomes a hinge, sort of. I can move this up. So while this was flat, this is no longer flat. Okay, so I can't actually extract a nice 4-uniform hypergraph where we can use Tibor and Victoria's construction somehow. And similar things happen for other groups. So this is actually very disappointing. But I think Shinichi mentioned earlier that he has a different proof of Walter's theorem, this picture theorem. So maybe there are completely other ways of proceeding for these other groups. Okay. And of course, you may ask, well, can you extend it to higher dimensions? Well, yeah, I'm not sure, but possibly. Okay, and the last two comments are sort of on the side. So we have characterized minimally flat symmetric structures, but of course, you would also like to characterize just flat structures. They're not minimally flat, okay? The problem is that some flat structures do not contain a minimally flat structure as a substructure, okay? So you really have to do something significantly new to attack that problem. And finally, maybe it's interesting to also develop a symmetry force theory. So this is sort of a big area of work in rigidity theory, where you just focus on motions that preserve the full symmetry of the group, of the original structure. So here you can ask, can you characterize all pictures that have a lifting that preserves the original symmetry? Okay, so you just extend your group to the higher dimension. And well, in the rigidity theory, this gives some nice results and methods. But maybe we can do something similar here. So lots of work still to do, but that's it. As a panel, as a body hinge?
No, in the plane, you only have an abstract hypergraph.
Yeah.
For uniform and symmetric.
Yeah. Mm-hmm.
So can you actually find a picture which realizes this structure? Because you want also, and you want the symmetry now refer also for length of the edge.
Not quite sure I understand the question. So what do you want to realize exactly? So what are you given? Or? Okay. Oh, well.
Such that the edges will be just the edges of the hypergraph will be a face.
Mm-hmm. Mm-hmm.
And then you can apply a number of C3 and
Mm-hmm.
get the same picture. Because you showed something about abstract graph.
Yeah. Yeah. Yeah, that's right. I don't know if you can always do it.
So if you have a four uniform micrograph which is symmetric with respect to C2, then you can have this result. I mean, if you start with a four uniform graph, you said the problem is the reduction to four uniform.
Yeah, right.
Other than that, everything else. For other groups.
Yeah, I don't know how to reduce the other groups. So, I mean, you change the lifting properties, right? Maybe I'm, again, not understanding the question, right? So.
I mean, if you're given a hypergraph,
Yeah.
so it's not for uniform, you do some kind of reduction.
Yeah, exactly.
So I'm saying if you start with four uniform.
Oh, then I think we can do the same. Yeah. I think so, yeah. Well, we haven't done it, but I think it's going to be pretty straightforward, at least, yeah.
So is the fact that you can't, so you give this example of the hyperagent size 5,
Mm.
which you can't reduce to hyperagent size 4. So is that similar to the phenomenon of trying to characterize flatness in things which are not minimally flat? Because the hyperagent size 5 in some sense is not minimally.
Yeah. Well, it is minimally flat, because if you remove any incidence, then I guess you can...
By the minimum count.
Yeah. But I think you can construct other examples that have a similar problem, and they're minimally... yeah, I don't think it's so much related. It's just it's maybe not the best example, it's sort of the smallest. But I think you can construct other ones that are problematic.
Okay, more questions? Okay, so the next talk starts at 3 p.m. Thank you again.